Hello everyone and welcome back to another question and answer session with the Paragon Space Development Corporation. I'm joined today with Barry Finger, the Chief Engineer of the Paragon Space Development Corporation. I'm Ryan MacDonald. I'm one of Mars One's astronaut candidates from the United Kingdom. Personally, I'm a theoretical astrophysicist working on a PhD in astronomy focused on exoplanets. So we've been receiving a number of public questions from people all around the world surrounding Martian life support and how the first few people living on Mars may actually just survive long enough to tell their tale. So without further ado, let's dive straight into it. Are you ready, Barry?
Yeah, I'm ready for some more good questions.
Excellent. So first question we received, so it's a bit of a follow-up from our previous conversation which we had back last in January. So at the end of our first interview, we talked a little bit about the importance of developing a prototype life support system which Mars One could then have inside of their simulation outpost so that the candidates training for the mission could gain familiarity with the system. So the first question though is that the astronaut candidates, in order to gain familiarity with this system, how long do you think they would need in order to become experts on how to maintain the systems and how to repair them?
Well, it's definitely not days or weeks. We're talking months or years of training, really, to get familiar with these systems, understand them inside and out, not only be able to operate them, but to repair them when they fail, or upgrade them and just do the normal maintenance. So, again, this would be like if you think of anything in your life that you deal with on a daily basis, and you have to maintain it, you've got to know the ins and outs of that system and hardware. So it's months to years of training, I'd say.
Yeah, so, and speaking of the maintenance though, we've mentioned a few times about the potential to use 3D printed parts in order to maintain the systems. So is it possible that in the years of operational testing, before you actually send any of the actual systems to Mars, that various components could be swapped out with 3D printed components to actually verify back here on the Earth whether they work or do not?
Yeah, I don't know if you remember from our study, we stated that we think 3D printing and additive manufacturing is important, but we wouldn't necessarily, Paragon, recommend you rely on that from the get-go. Having said that, if Mars One, if it helps them close their business case, if they want to push the envelope a little bit in that direction, I think it could help. But from the Eclipse perspective, we wouldn't require that or demand that be necessary, we think, to get going.
So we've talked about maintaining the systems, but I'm a bit curious now about upgrading them. So let's say you have 10 years of operational testing before you would actually send the first units to Mars. And so let's say during that 10 years, a new technology emerged which is maybe more reliable or more efficient. How locked in are we with the design of the Eclipse system as it stands at the moment? How readily could you upgrade it?
So good question. And it's easy to say, it's harder to do. But you want to design your system being modular, to be plug and play, to allow for upgrades. And I think that is important. And you can do it when you do engineered systems by defining the interfaces between subsystems or systems, making sure that those interfaces are well defined and don't change. Kind of like how a USB plug is a universal standard. And then people can make hundreds or thousands of different devices that use that same interface. So you've got to do things like that. But I do think it's important, if nothing else, even during the development phase, when you initially are building, you're not going to build the flight hardware right away. You're going to build flight-like prototypes and development units. Even there, we got to be able to swap those out during that testing phase we were talking about earlier in training. And then ultimately for the flight vehicle itself, though, design for upgradability is important. And I guess one other thing to say about all this is that you got to make sure you're not reinventing the wheel. Hey, just give me a little bit more money and I'll get you a 5% better improvement over that. And you're already at 95% efficiency, so now you're going to go to 96%. You gotta have a balance there.
Yeah, no. I mean, balance is just important for everything. Particularly, I mean, you can always throw infinite financial resources. That's the problem, of course. But at some point, you have to make a cut-up and decide what will actually carry out all the functions that we need for a reasonable amount of investment. And yeah, it certainly seems that we're following that approach. So that was a great first question we received, focusing on the actual technical systems of upgrading and repair. So now we've got a few questions about conditions on Mars. And so we'll start off with one about So someone is wondering about the effects that exposure to Martian gravity may have on the human body, and, well, whether that could have any design feed-in implications for the ECLSS life support system.
Yeah, again, I'm glad you gave that qualifier. I'm not really too qualified to talk about that from the physiological aspects. I can't see anything, someone's body changing in a way that how they interface or use or operate the ECLSS would be a problem. And then just speaking a little bit outside my area, just biomechanically, biologically, I can't see anything fundamentally different coming from reduction in gravity causing something catastrophic to the human system, if you will. I certainly don't see that with the electromechanical systems, the gravity being a problem. In fact, we'll use gravity to our advantage. So yeah, I don't think, I think there's an adaptation there, and it takes place over time, and people learn how to operate in that environment.
Yeah, so I've had a number of conversations with the Chief Medical Officer of Mars One, Dr. Norbert Kraft, about this, and he doesn't believe that there's any obvious. I mean, so just to reduce gravity, as far as we're aware, the body would just settle into a new equilibrium with reduced bone density, reduced muscle mass, etc. But nothing that would be fundamentally different, as you put it. I mean, if the greatest danger of Mars is not due to the reduced gravity, it's the radiation. That's what you have to be particularly careful about, and perhaps also the reduced solar incidence. You receive about 40% of the light on Mars that you do on the surface of the Earth, and so that might lead to, say, vitamin D deficiencies, for instance. But as far as I'm aware, the reduced gravity, which is about 38% of Earth's gravity, well, I don't see any long-term physiological problems for that. But of course, more research needs to be done on that.
Right. I guess if you try to come back to Earth, you might have some problems.
Yes, exactly. It's one of the distinct advantages of the one-way model, of course.
Yep.
So we've talked about the human system, but now we have a question about the ecosystem as a whole. So how far developed is the research of building ecosystems in space? Are there any serious considerations right now?
Yeah, so this kind of goes back. I think we talked about this a little bit. We hit on this in the report. Right now, as far as I'm aware, for human space life support, there's no serious active programs going on, what we call bioregenerative life support. But, again, I noticed last time, there's been a tremendous amount of work in this area. The U.S. has done this work. This is going back into the late 80s and the 90s and the early 2000s. But not just the U.S., the Russians, the Japanese, Europeans also. So a lot of work was done, a lot of publications, and that was on all aspects of bioregenerative life support. There's the growing the plants part. There's how you harvest those plants, but in a smaller scale compared to large industrial agriculture. There's the post-processing, turning the raw ingredients into foods. And so then there's even the bioregenerative side of recycling the waste mass from the plants, the roots, the stems, and the leaves, that if you have a truly closed environment, even that material gets recycled and turns back into carbon dioxide and the nutrients needed to grow the next crop of plants. So really a lot of work's been done there. And then since NASA's work and the space agency's work in the 90s and 2000s, greenhouse agriculture continues just to explode and expand. There's more and more money going into alternate crops, you might say, even, and how you grow those efficiently for the recreational enthusiasts. And but then in serious and for foodstuffs and growing plants in dense urban areas, lots of work is going on in that area to advance the state of the art there. So I just see a lot exists there to pull from.
Well, I mean, so in Mars One's case, they're planning at the moment to grow plants predominantly hydroponically. So, I mean, is it possible that you could implement into the system some kind of artificial soil, if you will, that could be used to this end?
Sure, yeah, and even with Boss Lonsdorf, we've talked about this. Making regolith, the Mars, what's on the surface there now, into soil, I think actually they did it on the Martian, right? And that
yeah.
it back. But it is, and it doesn't take that much. The regolith is this sterile, largely inorganic mixture of materials. So what is soil? Soil has carbon in it, has nitrogen, has those nutrients, it has water. So I think over time, if you have the volume and space, making a soil-based agriculture system could make sense, especially as you really grow the base over time. Sure, I see that's a good possibility.
Yeah, no, and actually, so Mars One has been working with a team of ecologists over at Wageningen University, actually, They've been investigating growing Earth plants in what is effectively a Martian regolith simulant, for instance. And they regularly post updates to that over on the Mars One community pages. So there's still very interesting research going on this right now. So I suppose we'll have to see. But I'm certainly excited to see how easy it would be to take Martian surface material and just turn it into soil. But again, it's something that I imagine you wouldn't rely on it, but instead you would have, say, the first settlers using hydroponics but experimenting on the side with trying to make a soil simulant.
Exactly. Yep. Again, I think I said it last time. I really see these people that go and stay. They're like farmers. That's literally their life. Their life is about, eventually it gets to that point where they're taking care of themselves. They're constantly finding better ways to do things, making do with what they got, and then making better for themselves is finding if you can find a more efficient way to grow plants, and if it made you be able to use less water, for example, and then you could have your buffers of water increase in other areas, so you're not tied up in hydroponic systems. I think that's the way it will progress.
Yep. So another question now we have about conditions on Mars, and I'll tackle this one. So we've had a question in what the normal surface temperature of Mars is in Fahrenheit. So basically, it varies extraordinarily due to Mars's very thin atmosphere. If you're just talking on average, roughly about minus 67 Fahrenheit or so. But if you're on the equator and it's a very warm day in the summer, maybe about plus 68 Fahrenheit. But if you go down to the poles on the southern or northern hemisphere, then you're talking more like minus 240. So huge temperature swings, which is why in Mars One's case, for instance, they're looking at effectively a trade-off latitude of about 40 to 45 degrees north, because the further north you go, the more water ice there is, which, as Barry will attest to, is absolutely vital for the Euclid system. But then, obviously, it's hotter, and then that makes everything work slightly better. You receive more incident light from the angle towards the equator. So that's roughly what goes into the decision. But yes, so the temperature swings dramatically, and you have to design the equipment accordingly for that.
I think that's what the big challenge there.
So now we have a question about the energy storage requirements for powering the life support system. So what would be the energy requirements to run the life support system during the worst case scenario of, say, a 6-month duration global dust storm? And then we'll have a follow-up question after that.
Yeah, so I don't have the exact numbers off the top of my head. We have to pull from the study, but we talked about that, and we actually didn't look at it from the dust storm perspective. We were looking at what's the shortest solar day or sol on Mars, and how much energy could you make it in that day. And I think to the question though, you've got to know what those things are. So we got that down about what's the longest day, what's the shortest day. So those are the things to start designing to. And again, I'm not the power expert. I'm not the solar array expert. I'm not the Mars dust expert. But my understanding is that even on a bad dust storm day on Mars, there's still quite a bit of incident light that hits. And so it's so say you take a 40% hit, then that is the number you have to design to size your arrays to get through that period. So in other words, you may end up on I don't know, 3/4 of the time having way more solar power capacity than you need, and that's the kind of a price you pay then to be if you're going to rely on solar to get through the worst day that you can experience. So I guess that's what I'd say right now. Is it goes back to that the people responsible for designing that system to make sure they know the requirements, what's going into sizing it, so they can prepare for the worst case.
Yeah, and again, it's what we discussed a little bit last time about how you need all of the different key teams working on the different actual key components for the mission to be talking, communicating, and liaising with each other. Obviously, as yourselves focusing on the Eclipse, you can say how much electrical power you actually require. And it's up to a different team to then go away and say, right, this is how much the Eclipse needs, this is how much the living module needs, etc., etc., etc. During a global dust storm, it varies a lot. You can get localized pockets of regions with a dust storm with an optical depth of 5 or so, and then you're talking more like you're receiving about 1% of the incident light that would be hitting the top of the atmosphere. But those events are extremely rare, and they're only in very localized places. And truly global dust storms are actually extremely rare. As far as I'm aware, there was one back when Mars 2 and Mars 3 went to Mars in the 1970s, but the global dust storms of severe magnitude are extremely rare. So,
Was that Mariner 1 and 2, you mean? Mariner 1 and 2 spacecraft?
Oh, no. I was looking at Mars 2 and Mars 3, the Soviet Union's missions.
Okay.
Yes, no.
One other thing to say on this is just, we talked about this in our study, but the idea of building up buffers in the system, there will be those times when you've got to hunker down and kind of get through the cold winter night, so building those buffers up will be key as well. There's some amount of time we can weather the storm, so to speak.
Well, speaking about buffers then, so buffers in terms of being able to have replacement parts to repair systems, for instance. So what sort of spares inventory do you expect the life support system to have?
Yeah, so when we did our conceptual design, you have to make assumptions. And I believe the numbers we had were about 25 to 30% on average, depending on the system. Some are more mature and have longer lives and better demonstrated performance. But on average, we assumed about 25 to 30% of the mass we ship for spares. And so it kind of gives you a starting point. And again, remember, we're at a conceptual design point, so you got to start refining those numbers as the design matures. How long does that really get you? And then ultimately, it is, what are you doing with that mass? And what are the actual? We talked about that again too. That the way we have done it now in space isn't necessarily how you would do it for the Mars 1 mission.
So, of course, if you want to be sustainable, you need to be able to extract resources from the Martian environment, and crucially one of them would be water, which you can extract from the Martian regolith. So in your design assessment, you had a component called a regolith hopper. It's effectively vibrating and shaking regolith, and it's where the regolith is actually being fed into the life support system. But humans are not on Mars from the very first day. The outpost has to be able to operate autonomously without intervention for the first 2 years. And so one question that I've had now is about, what do you do in order to prevent the regolith hopper from clogging before the first humans arrive?
Good question. And again, this gets to the whole concept of, we're talking about what has to really happen. You have to design and build very reliable machines. And that really is what it comes down to. And so you do have to understand the environment. You have to know what the wear points are, what are the failure modes. And so it's going to take a lot of design work. This is the non-trivial parts of all of this is non-trivial, but it's down and dirty, I guess pun intended, engineering and operational testing that has to happen to build these long life machines. So it's a serious undertaking. I guess one thing I note though is, I would want people to think of like large scale terrestrial mining applications. I think it's something like 8 or 10 cubic feet of material a day we're talking about needing to collect. I think we assume 5% moisture content in the regolith. And so when you do the math, it's not a huge amount of material you have to move every day, but you do have to process that material every day. So there's lots of detailed design work to do there. And I'm thinking of the Curiosity rover. If people have seen videos of that and still pictures now, and still pictures really, but they're getting wear where they didn't expect it. Some of the metallic wheels that they use are getting worn through. So we'll be learning. Mars 1 has to learn from all those sources of information what we're already getting back now, and making sure that and there's a lot of work. If you just go to that, you just look at that one thing with the Curiosity rover. And I don't know if you've seen that, Ryan, but
yes, I've seen the holes in the wheels from going over the rocks, etc.
So to go do this mission, we can dive down here just a little bit. Mars 1, really, it's not just you're going to go notice that on a video screen. You're going to go to NASA. You're going to find the engineers that designed that. You're going to learn the details about how thin did they make it, what was the issues, what did they encounter. So right there is a tremendous amount of work that has to happen. But you can define that scope of work and go figure those things out. And that's just one example of like the applied engineering aspect where you can go to do a mission like this.
Definitely. So, I mean, we've just been talking about how parts break, they're not working all the time, and so just like with the Curiosity rover's wheels, etc., this will also be true of the life support system. So, firstly, how often would maintenance of the life support system have to take place, And do you know how many parts would have to be replaced as part of this maintenance schedule?
Yeah, so it's kind of I'm not gonna have all the answers entirely right now at this point. I think first of all the thing is remember the system has to operate autonomously before the crew gets there. We have to have full tanks. We have to have water. We have to have tanks of compressed gas for storage. We have to have a pressurized habitat. So all those things have to happen autonomously. I imagine there's some ability for the equipment to maybe do some type of robotic repair of some components. But so that's the first thing is the system has to be designed for autonomous operation from the outset. So maintenance, and again, I'm sorry, I'm not going to remember all the numbers off the top of my head, but we did talk to maintenance. We think it has to be such that they're not every day trying to fix this thing, but it will be regular, sustained maintenance once you get into operations and the crew is there. That again, their job, if you will, is keeping those systems alive and operating and functioning normally and nominally, and hopefully getting good enough at it where they have free time and they have recreational time. But again, if I use the farmer analogy, farmers are known to be very hard-working people, and that's what their life generally is about is working. And so that will be the life of the initial Mars One inhabitants.
So obviously, if there is an incident and say one of the parts breaks, for instance, you can obviously replace it as part of the maintenance schedule. But then there's the question of where these parts are coming from. So we talked previously about how you were originally anticipating about 25 to 30% mass equivalent of the ecosystem would be devoted to spare parts. But is it possible that some of these replacement parts could be manufactured using local Martian resources via 3D printing?
Yeah, so again, I think eventually that's the possibility. Again, if Mars One chose to implement that earlier, put some money into that, and ultimately some launch mass to get the system there to do that, I think it's possible. We would definitely take advantage of that if it came to pass. But again, our position is we wouldn't want to propose to rely on that at this point, because my concern would be that then it'd be another reason to wait to not begin the mission because the technology isn't ready yet. Technology to do that in manufacturing.
I mean, ultimately, it's obviously important in the very long term, because in the very long term, you want to be self-sustaining and not be reliant on regular resupply shipments from the Earth, of course. So it's a big step up, obviously, that you can certainly ship the basic feedstock for a 3D printer and then use that on Mars. And that would be really good to do for initial testing of the 3D printers. But no, I completely agree that if you want to be sustainable in the very long term, you have to experiment and then find a way to use Martian resources to do this. So, I mean, Mars One can't plan to do this initially because you don't know whether you can or cannot do that. But it can always be one of those, once we have one or two crews down on the surface, they need to be experimenting on how to extract certain resources, doing the chemical analysis of the regolith, etc. So I imagine that will come later on. But no, I completely agree with the person who asked the question that you have to examine this for long-term sustainability to even be possible.
Definitely. I agree 100%. Yeah. Long term, that's where you'll be.
So now a question about Paragon as a company. So have you had any input to the design, construction and maintenance of the life support system on the International Space Station?
Good question. So the answer there is Paragon is made up of engineers and scientists and technicians that come from other jobs. So there are some of us that have worked for other companies that have worked space station. The president and CEO of our company helped design some of the solar array systems for a space station when he worked for Lockheed Martin. I previously worked for a company called Honeywell. It was before that called Allied Signal. And there we developed part of the life support system, CO2 removal system, lots of parts and pieces in the internal thermal control system. And as a younger engineer, I played my part in some of those roles. On the maintenance side, I personally managed what Honeywell's sustained engineering program for ISS. That's where once things were up and operating, but breaking down, how working to get those repaired, keeping them up and operating. So we have that sort of experience that comes to our company. Then on the other side, is just as an aside or whatever, we're in a very rare crowd, is what I'd say. When you think about how many spacecraft actually been built, there's not that many. It's nothing like cars or boats or planes. It's a very limited number of spacecraft that have been built. But we have hardware that flies on the Orion spacecraft, the first one that went up as a test vehicle. We're built manufacturing hardware now that will go on this next vehicle. Some of it's not that exciting. It's tubing and ducting and pieces of plumbing. Some flow. We have another system that's a flow bench, and it measures parts of the internal thermal control system, pressure in the spacecraft. Then on just commercial crew side, NASA has a program you guys have heard, I'm sure you're aware of, to bring crew commercially to the space station in the next couple of years. On the Boeing spacecraft, we build the humidity control system for that. And so yeah, we just won a contract actually on the space station's water recycling system. There's one part of the water that's not recycled right now. It's a brine that's generated from processing urine. And it's the last big step to close the water loop to approach that 98, 99% water recovery. And we just won a competition, a down select, to build that system. And literally today, I just was part of the first meeting with NASA to start talking about the requirements and safety review panels and what it's going to take to fly this safely at ISS and operate it. So as a small company that's doing things in space, and we're pretty excited about what we've done. A lot more to do for us as a company, and what I always tell people is when Mars One undertakes a mission like this, it won't just be Paragon that on the life support side that'll make it happen. It will be an entire team of people across really probably the planet by the time it's done, the contractors and expertise that they've brought in to bear to go make the life support system happen.
Well, firstly, congratulations on winning that contract. That's absolutely great news. And yeah, no, you're absolutely right. It's one of the big advantages that Mars One has by being a truly international organization and not for profit as well, that they can just pick and choose the best teams from around the world to put together a truly global effort to make this happen. So it's one of the things really unique about the approach they're taking.
Yep, I agree.
So now a question, though, about a potential emergency situation. So we use storage tanks in order to create the buffers. We've discussed this previously. So you would store spare oxygen, for instance. You could also store spare CO2 if you want to blow off just dust when you go through the airlock, for instance. So what happens if one of the storage tanks breaks? I don't know, they might be hit by debris or leak, for instance.
So it's a bad day. So you call it a bad day. So again, we talked about this in our study. I know I'm probably repeating myself now, but buffers are very important, and we talked about it in terms of the solar storm earlier a few minutes ago, or not solar, but a dust storm to get through. Well, this is another thing. You've got to have buffers built up in your system because things like this will happen unexpected. They're not planned for, and someone might fall and puncture it. You don't have to have a meteorite. So the key though is to have distributed buffers. And again, you can think of this in lots of scenarios where you don't put all your eggs in one basket. That's saying in America. I don't know if they have that over there. But the idea is it's not just one tank of water. It's not just one tank of gas. So if you remember what we're doing, the model is we fly two complete eclipses down to the surface. They're both building up right from the very first mission. They're storage buffers of oxygen and water, primarily, and atmospheric gases. And even in that implementation per eclipse, if you will, you're probably smart to get those tanks distributed, have them manifolded in a way that maybe they're plumbed together or they're isolated and can be plumbed together. So you have to have the valving and stuff like that. So I think that's the key, is building up buffers over time and making sure they're available.
Okay, so we've talked about a bad day, or maybe we'll call it a Mark Watney typical day, for instance. So so let's say something's broken and then you need to repair it. So you can obviously anticipate these situations because things won't work perfectly for all time. So in your design process, how does easiness to repair contribute to the process?
So yeah, good question. This is one of my true things is of how I think as an engineer. I think that's hugely important. How easy is it to operate? And an example I use when I talk to people about metallic pressure vessels, a spacecraft hull, if you will, or the pressure vessel on the surface of Mars that's keeping a nice bubble of oxygen in the air inside and prove safe in the vacuum on the outside. If you did get a hole through that thing, would you rather have this metallic can that's been penetrated, and you picture a projectile going through a piece of metal and bending it and making this hole, this gaping hole, and trying to seal that? would we think of a soft goods type structure, where it's not like a balloon. Don't think of these soft goods as balloon, but as I don't know, the liner in a pool or something, that one of those soft-sided pools. You can just put your finger over it and plug the hole. So I guess that's not a great example, but building systems that are low pressure, near ambient temperature, they may not be quite as efficient. They may take a little more power or a little more room, but they're repairable by lower level technology, if you will. So yeah, you could have this great device, and it runs at 900 degrees Celsius, and it has a titanium alloy vessel. But when that goes bad, and there isn't another one on Mars, that's a really bad day. So I look for ease of maintainability as being an important part of how you ultimately select your technology and how you implement your technology.
So we've talked a lot about the life support system in the near future and how you actually just keep people alive in the short term. But now a question looking more to the longer term. So firstly, what are the key requirements to enable Martian life to be fully self-sufficient and completely independent from the Earth? And do you have a rough estimate on when you expect this might be achieved?
That's a great question. That's the whole enchilada right there. But if I had to go in order, I'd say it's like this. First thing you need is pressure vessels that don't leak. You've got to have an atmosphere. Humans can't live for any length of time without a pressure vessel around them. You've got to have energy to drive the systems that power your life. And whether that's using solar directly, maybe for some plant growth eventually, or photovoltaics or a nuclear power plant, but you've got to have that. You've got to have water. Water is the stuff of life. It's what most of us are made. It's most of what we're made of is water. You've got to have access to that. And then the next thing for this long term, you absolutely, positively have to grow your own food. If you have to import all your food, if you have to end up having machines that produce oxygen and water purely physiochemically, I just don't see that for the long term. At least it wouldn't scale. It'd be so hard to scale up your number of people. At some point, it's purely living in a mechanical world where everything is made by a machine. I struggle with that. So you had another question about the biology. I talk about this a lot, that the 3.5–4 billion years of evolution has taken place, and the micro machines, the biological machines that have been created over that time and matured and evolved, and the countless versions that have come and gone because they weren't efficient. There's so much engineering there, if you will, to build those machines, those biological machines. It just makes sense to use that technology. And it is think of it like a technology. And then finally, I guess we talked about the additive manufacturing, but the ability to manufacture and place almost everything you need, or you got to provide something that other people are willing to pay for, and maybe then you trade for some of those things. So maybe you don't build microelectronics on Mars anytime soon, but you're trading something else. I don't know, what that would be.
Well, my idea is that perhaps the main export from Mars will be ideas, because you have people on the surface conducting scientific research experiments. There'll be PhD theses back on the Earth that rely on people carrying out that work on there. So I imagine there might be some kind of trading of resources going on between university departments back on the Earth who want to have certain research conducted by the people on Mars. And that's great because ideas travel at the speed of light. That's the only limit that you have. Because I can't imagine it being economically viable to ship material from the surface of Mars for a very long time. There's asteroids if you want to do that viably. But ideas, I can see that as being a key export.
Yeah. And yes, on timing, I think I'm an optimist. I wouldn't be working on this program if I wasn't. But I'd say if they really got going from the time of the first landing, and they sustain, the business model allows them to bring new people down in a regular basis and expand the base. 50 years, it's not like the second mission. There's one thing to be clear. It's not a second or third or fourth, but 50 years of missions, something like that, maybe the 25th mission. Maybe you're really getting self-sufficient at that point. I don't think it's hundreds of years.
It depends a lot on the model, of course, because that's assuming that you always just send a new crew of, say, 4 people every 2 years or so. And my personal vision is that Mars One would serve as a catalyst, and that by exciting the world with the first few missions or so, it would lead to more funding and more investment going into it, and more people wanting to go to Mars. And obviously, we know that Elon Musk has his long-term plans to put large numbers of people down on Mars in, I don't know, whatever decade it may be in the future. So I would like to hope that that 50 years can be a linear extrapolation from current technologies and current ideas on what we need for sustainability. But who knows? Because if you expand an exponential function for small values of x, it looks linear. But it's only when you start going 10 years in the future that you can finally see that you're on an exponential trajectory. So we'll just have to see.
Okay, I agree.
So now we're getting close to wrapping up the last 3 or so questions now. So now a question about the extravehicular activity Mars suits that you've also been looking into for Mars One. So have you considered having the EVA suits externally attached to the habitat and entered through a suit port, which would reduce the amount of atmosphere that would get lost every time you would, say, cycle an airlock in a more traditional model?
Yeah, good question. And again, you said suit port, so you're probably aware, and whoever had that question probably aware that NASA has a program, a project called Suit Port, and it's a way of looking at just that. For me, just looking at this, and I love again, great people that are developing the suit port, incredible technology, and making it happen. I do see some of the challenges they have is trying to keep that you talk about interfaces. There's an interface between the suit and the spacecraft or the habitat. Try to engineer that elegantly where it doesn't look like a big patch on your back and move around with constantly. There's a lot of work that has to happen there. So I think there's some challenges there just on the engineering of that. But the other thing is for the Mars One model, no matter what, you're going to have to do maintenance on these suits and systems, and you're going to have to bring them in. You're going to have to bring them in at some point and do that. If you look at it purely as an airlock cycling method to save gas losses there, I think again there could be other ways to do that, reducing the size of the airlock, regenerating, pulling the air out with a vacuum pumps. There's some things you can do, basically walking through inflatable volumes that minimize the volume of the airlock. Now, the dust or something like that, to minimize how many times you have to clean up dust and you're bringing that in the environment, that is a possible reason I think you don't want to pay that tax, if you will, or put the suit port in. But so I think the jury's out on that. I know our subcontractor that we use to run the suit system, they build components that are part of this, developing components that are part of the suit port system. So I think that's open right now in the trade space.
Okay, and a follow-up on that one, though. So you said that the Mars suits eventually would need to be brought in so that they can be repaired or maintained, for instance. So do you have a target operational work lifetime for the Mars suits?
Again, we're going from memory, but it was about, I think we for a single-use EVA, we figured 8 hours of operation was remote. And I remember Mars One thinking that might even be on the long side, driving to a more extreme solution. In our total lifetime for an individual suit, we assumed we'd have to achieve about 250 cycles for that suit before it needed to be replaced.
Okay, and we'll wrap now with the final question. So we talked a little bit about this earlier, about dust storms, for instance, the influence on the life support system and whether you would have sufficient power. But let's say that you were in a situation where the life support system did not have enough electrical power to run. What are the contingency plans for dealing with such a situation?
Yeah, so it's a good question. And again, those things will happen. I feel like the things will happen you don't plan for. And so it's kind of like at the beginning of the mission, the first one, when your buffers are the smallest as they're ever going to be, it's probably going to be the most dangerous time. You'll have 2 pressurized volumes for the habitat. You'll have a few other structures, the landers for the Eclipse. And again, say you had 2 water tanks per Eclipse or something, you'd have 4 total. You're going to be limited there a little bit. But the idea is that you have those buffers that you can live off of, that you can tap into. Again, that movie, The Martian, they had some good things where he went into his former crewmates with the items they had, food items and things, and made use of them. So again, I guess the answer is that buffers are the key. Buffers will be the key to life. Whether you're getting over a normal winter, maybe there'll be a certain time of the year the system just won't make enough power, and you have to pretty much power down your ISRU system. your oxygen production system for 16 days to get through the shortest part of the winter or something, you're going to have buffers that allow you to get through that. And again, in human existence, and I'm definitely not a student of human history, but you just think of settlers and get, preparing for the winter and working hard through the spring to get their stocks of food stored up. That same type of philosophy will apply in the Mars One case, I believe.
Well, it's a very positive note to end on, how there's no limit to really what we can do with the human spirit of pioneering, working hard, and trying to get through any problem that can be thrown at you, and bunkering down and getting through the hardest days. That will be true just on Mars as it is on the Earth, right here. So then, that's all that we have time for now. Thanks again for everyone that sent in these wonderful questions. If you do still have more questions that you might be interested in seeing either Barry or myself discuss in future, you can either submit them on Paragon's website. You can also send them to Paragon over Twitter at ParagonSDC. You could send questions to me either by commenting down below on this video, finding me on youtube.com/MartianColonist, or on Twitter at MartianColonist. But for now, goodbye. Bye.